Course 3: Industrial Processing, Resource Efficiency and Waste Management in Food Systems, Waste Valorization and Circular Economy. This module introduces the principles of raw material control within industrial food supply chains, focusing on how sourcing decisions, raw material quality, and supply chain dynamics affect processing efficiency, food safety, waste generation, and sustainability performance. It examines industrial supply chain structures, upstream-downstream dependencies, and sourcing models, with particular attention to traceability, regulatory compliance, and supply risk management in the European context. The content addresses practical approaches for evaluating raw material usability and value, including physical, chemical, functional, and economic criteria, and explores strategic sourcing and inventory control methods to improve resource efficiency and resilience. Material flow analysis is presented as a key tool for mapping inputs and outputs, identifying loss points, and quantifying food loss and waste in processing operations. Best practices in raw material handling, hygienic design, process standardization, and operator training are discussed alongside strategies to reduce avoidable waste and manage unavoidable byproducts. The module also introduces waste valorization pathways and circular economy principles, including energy and water-efficient technologies and cross-sector reuse options. Digital solutions for waste monitoring and inventory optimization are highlighted as enablers of data-driven decision-making and continuous improvement. After completion, learners will be able to explain circular economy principles and describe energy and water-efficient technologies for improving sustainability in food processing. The circular economy represents a shift away from the traditional linear model of take, make, and dispose. Instead, it aims to keep materials in use for as long as possible, minimize waste generation, and regenerate natural systems. In food processing, circular economy principles focus on improving the efficiency of raw material, energy, and water use, while reducing environmental impacts. Traditional food systems are largely linear. Raw materials, energy, and water are used once and then discarded as waste. This approach leads to high levels of food loss, inefficient resource use, and growing environmental impacts. Circular economy approaches aim to address these limitations by rethinking how resources are managed throughout processing operations. The circular economy is built on a small number of core principles. These include preventing waste at source, extending the useful life of materials, and recovering value from unavoidable waste streams. In food processing, this means closing material, energy, and water loops while balancing environmental and economic performance. In circular food processing systems, material flows are redesigned so that byproducts and residual streams are reused or valorized rather than disposed of. Redirecting these flows reduces reliance on virgin resources and improves overall processing efficiency, supporting both sustainability and cost reduction goals. Energy consumption is a major environmental and economic factor in food processing. Thermal operations such as cooking, drying, and sterilization are particularly energy-intensive. Improving energy efficiency is therefore a central element of circular economy strategies, reducing both emissions and operating costs. Heat recovery technologies capture waste heat from processes such as cooking or pasteurization and reuse it elsewhere in the plant. This reduces fuel consumption and improves overall energy efficiency. Heat recovery is widely applied in food processing facilities with significant thermal operations. Process integration focuses on aligning energy supply and demand across different operations. By matching processes that generate excess heat with those that require energy, facilities can reduce total energy input and improve system-level efficiency, supporting circular energy use. Thermal operations can be optimized through better control systems, improved insulation, and optimized operating parameters. Continuous monitoring helps identify inefficiencies and minimize energy losses, contributing to more sustainable processing operations. Integrating renewable energy into food processing operations reduces dependence on fossil fuels. Technologies such as solar thermal systems, biomass boilers, and anaerobic digestion convert waste streams into usable energy. On-site generation improves resilience and supports circular economy objectives. Water is a critical resource in food processing, used extensively for washing, cooking, cooling, and cleaning. Inefficient water use increases costs and environmental pressure. Circular economy approaches aim to reduce freshwater demand through efficiency and reuse strategies. Water-efficient technologies include closed-loop systems, safe reuse of processed water, and high-efficiency cleaning methods. Monitoring water consumption helps prevent excessive use and supports improved environmental performance across processing operations. Wastewater from food processing often contains recoverable resources. Treatment systems allow safe discharge or reuse and may also recover energy or nutrients. These approaches reduce environmental impact and support circular water management. Energy and water efficiency are closely interconnected. Reducing water use lowers the energy required for heating, pumping, and treatment. Integrated strategies that address both resources simultaneously maximize sustainability benefits in food processing. Circular technologies offer multiple benefits, including lower operating costs, reduced environmental footprints, improved compliance with regulations, and enhanced resource security. Together, these benefits support the long-term sustainability of food processing operations. In summary, the circular economy replaces linear models by focusing on efficiency, recovery, and regeneration. Energy and water-efficient technologies play a central role, and integrated approaches deliver the greatest sustainability benefits in food processing. Thank you.